Anyone who has sat through elementary school math remembers the friction of rote memorization. The lower tables are manageable, but when you hit the nines, the cognitive load spikes. To bypass that memory strain, you can offload the calculation of 9 times 8 directly to your hands. The setup is simple. Hold both hands out in front of you, spreading all 10 fingers wide, mapping them sequentially from 1 to 10, reading left to right. Because we are multiplying by 8, count to the 8th finger, your right middle finger, and drop it. This single movement splits your remaining upright fingers into 2 distinct groups. To extract your data, look at the group on the left. You have 7 fingers standing. On the right side of the dropped finger, you have 2. Put those digits together, and you have 72. Your hands have successfully processed the equation like a standalone mechanical calculator. It looks like a simple shortcut, but we have to ask why the mechanical action of folding a finger generates a correct 2-digit mathematical output. This alignment between anatomy and arithmetic is a structured result of how we've organized our numbers. It is an active demonstration of embodied cognition. This is the process where we use physical movements to substitute for internal mental processing. Instead of forcing your brain's working memory to recall an abstract fact, this algorithm shifts the computational burden onto your motor and visual pathways. You aren't performing magic. You are physically manifesting a mathematical law that is built into the way we count. This physical exploit works because of the architecture of our base 10 numerical system. Take a look at this equation. There are 2 principles at play when you multiply a single digit by 9. The first is the tens digit rule. The tens digit of your answer will always be exactly 1 less than your multiplier. Apply this to our equation. We take our multiplier, 8, subtract 1, and we generate a 7 in the tens column. The second principle is the rule of sums. For any single-digit multiple of 9, the 2 digits of the final answer must add up exactly to 9. Our 7 plus some unknown number must equal 9. Mathematically, the 7 demands a 2 to complete the sequence. That locks in our final output of 72. Now, map those rules back onto your hands. When you drop your 8th finger, you are visually subtracting 1 to leave 7 fingers on the left, which leaves exactly 2 fingers on the right to complete the total set of 9. Our biological symmetry, possessing exactly 10 fingers, creates a calibrated physical interface for navigating the logic of base 10. But this interface requires strict adherence to its rules. The system fails if you reverse your directional sequence. If you initiate your finger count for right to left, dropping the 3rd finger from the right edge, you generate an output of 27. The mathematical data is incorrect for this specific equation. This chart illustrates the place value orientation of base 10 mathematics. The system dictates that larger magnitude values, the tens, must precede smaller values, the ones, strictly reading left to right. Physical mathematical exploits are only functional if we force our organic movements to obey the directional laws of written numerals. This synchronization between our bodies and our math extends beyond classroom shortcuts. Looking at this schematic, we can see how the anatomy of a hand maps over a traditional abacus. The way we use fingers to group tens and ones follows the same logic as early mechanical data registers. Using physical space to separate data streams, just as a single bent finger creates a boundary between tens and ones, parallels the way mechanical devices organize information into columns. The hand serves as a biological register, holding and manipulating data through the physical arrangement of the digits. Calculating 9 times 8 on your fingers is a direct execution of algorithmic logic, performed by the hardware you were born with. Ultimately, this trick shows that we shaped the rules of base 10 to fit the 10 fingers we use to count, making the body an integral part of how we process the world.